finite word length and its effect. Before starting that, we should be aware with a little bit basics, which I think you already know, but just a revision kind of thing in case of numbers and all. Why? Because there may be a question asked on a fixed point or floating point numbers. Okay. So what we know, we can represent any number, let us say capital N, to any desired accuracy by a finite series. Because we know how to represent the number, but generally what is the formula which we don't remember is something like this. Capital N is equals to summation over I equals to N1 to N2 CI where R is to I, where R is called as radix, right? Let us say if your R is 10, we are calling it as a decimal. If it is R equals to 2, we are calling it as a binary representation. Now, when you have the number, let us say 30.285, and using this formula, if you see, definitely you can rewrite your number something like this, right? Because here you can see this is a binary point, decimal point, left to which we have an integer part and right to which we have a fractional part. So this is 0, this is 1, 10 power 0, 10 power 1. This is 10 power minus 1, 10 power minus 2, 10 power minus 3. So if you put together, you will get the same number, right? Same way you can do this kind of thing with your binary number. That means uh, we can as a human being when we are interacting with each other, we use a decimal numbers. But when you want to interact with the system, we want binary representation. In your STLD, you have studied the conversion of your DC to binary, binary to hexa, and so on. Right? So we are not going into the STLD now. Simply, I am saying that we know how to represent the number. The number may be a decimal number or a binary number. Now, as our aim is to study DSP, in the DSP, we are discussing about how the processor manages to deal with the number representation. What kind of number representation we can do when we are dealing with the digital computers or digital hardware. That means whenever we are representing a number in digital computer or any other digital hardware, we can use any one of these form. The first form will be you can either represent with a fixed point number. Next, you can represent with a floating point number. And third one, you can we can represent with a block floating point number. So in this today's class, we are going to see only of what is fixed point representation and floating point representation, right? So I repeat, we know how to represent the number. This is the with a finite accuracy. This kind of formula. If you use this, we can get any number, decimal, binary, depending upon the base which we are dealing. When we are dealing with the digital computers, we want to see how these digital computers or digital hardwares uses number representations. So that number representation can be your binary fixed point form or floating point form and so on. Now, in this fixed point representation, floating point representation, and block floating point representation. Now, what I'm talking about is fixed point representation and all, like I'm dealing with the processor. Inside the processor, we will have some registers, right? Now, how those registers are programmed, because every time we are not saying this is my integer part, that is my fractional part, and something like that, right? That means when we are writing the algorithm in such a way that, or when we are dealing with the processor in which the point position is fixed in the processor, and the point if the point position is fixed in the processor, then we are calling it as fixed point representation. That means here I can say, let us say if I write the decimal number 1.75. So what I am saying that this is my decimal point, left to which I have an integer part, right to which I have a fractional part. Now this point is fixed when I am writing the algorithms to work on your DSP or digital hardware. I have some length of bit register. In that, we are programming your register in a such a way that first 4 bit you consider as a integer part, next 4 bit as a fractional part, and throughout the position of that point will be fixed. It will not be changeable. So that is what we call it as a fixed point representation. In case of binary representation, you can see this is what your binary point. Again, left to this is your integer, right to that is your fractional part. Means in short, can say whenever the position point position is fixed in the processor, we call it as a fixed point representation. Now, in case of fixed point representation, you people can see like same like in STLD when you have some number which we are representing in a binary, you can use we want to represent the number either with sign, that means plus number, the number will be plus or minus, right? So we have different forms to represent negative numbers, because there is no issue with the positive numbers. When we are talking about negative numbers, we may talk about sign magnitude form, one's complement form, and two's complement form, right? This is only a record, a good to know information. We are not going to deal all that over here. Simply my aim is to say about we are dealing with a digital computer or processor which is having some registers. The registers accepts or it will be programmed. It has algorithm in such a way that whenever we are representing any number, when we are writing any number, how to take that number, how to get represented inside. That is depending upon the position of the point. If it is fixed, it is a fixed point. If it is not fixed, it is called as a floating point. That's it. So now in this fixed point representation or floating point representation, I will be bothered about addition, multiplication only. Why? Because if you remember, when we talk about any digital filter or any digital system, what we will do, we will we will have a delay element. That delay element will get multiplied with some coefficient, and then afterwards it will get added. Means ultimately, whenever you are realizing any digital system, in that you come across a delaying, a multiplication, and the addition. So that's why other calculations we are used further. Only we focus more about here addition and multiplication. Now, as your computer use either uses a fixed point or floating point. Now, if I use fixed point, how to do addition and multiplication? If I use floating point, how to use addition and multiplication? That is my task to see today. Okay, let us say
Excuse me,
addition of
ma'am.
hello.
Ma'am, your audio is having some disturbance, ma'am.
Yes, ma'am. Your voice is also got low, ma'am.
Okay, okay. Uh, hello, hello, hello,
Yes,
hello.
ma'am.
It is okay now.
Ah,
Hello.
yes. Okay,
Oh,
ma'am.
okay, okay, okay.
Thank you.
I'm not seeing. Now I was talking about the addition of two fixed point numbers, because as I said, I'm interested to see about to see about the multiplication and additions, right? What we know when we are adding two, because this is what the mathematics which we have used to, like how to add the two numbers, two fixed point numbers. Let us say I have taken your two number. Let us say I'm adding this 2 and 8. Okay, this is for decimal. Am I audible now?
Yes, ma'am.
Okay. When I'm adding 2 and 8, I know the answer will be 10. This is my Daisy addition. When I'm going to do binary addition, so definitely I am writing like 2 binary equivalent and 8 binary equivalent. Now here you can see something like that also I have written. Because from this what I can say is, when I am dealing with the processors, and now in that processors I'm dealing with registers. The registers are of 8-bit long. Okay, in that 8-bit long, the algorithm is written in a such a way that the first four point will be an integer part and rest 4 point will be a fractional part. Okay, so therefore, though the number I can see 2 and 8, I should write I should write 2.0 and 8.0. Therefore, because the 4 points for 2, rest 4 points for a fractional part. Same way I have to do with your 8 also. Okay, so now in this we know addition how we are going to do. So this is how you will get the addition in when you are talking about the two fixed point number. Means when your number is of b-bit long, make a note, when your number is b-bit long, b equals to 8 bits, here b equals to 8 bits, you may get answer equals to 8 bits. But sometimes when you are adding the number, like what number I can say here, wherein you got 1 over here. Okay, 1 over here means when you are adding the two b bits, and the result is b plus 1 bit. Result is b plus 1 bit. Means I can say, let us take one more example. Let us say 10 plus 8. What we know here, there is no problem. Here in all additions you have done. Now coming to this, whenever there is a carry, whenever there is a carry generated from the MSB bit, then now if you see the total answer, it is of 9 bit long, right? I have been with b equals to 8 bits, b equals to 8 bit, and my result is now b plus 1 bit. 9 bit result is I am getting over here. But what if my register length is of only 8 bit? That means this 9 bit I got extra one, right? So that is what the problem is. In most of the when we are dealing with a number wherein you don't get carry generated from the MSB, in the cases where the carry is not get generated by the MSB, there is no problem of overflow occurs, because this all is studied in your microprocessor, right? But whenever we are dealing with the two numbers in which the MSB carry will get generated, that means when we are going to add two B bits, your result will be B plus 1 bit. So at that time the overflow occurs. So that is what one problem which we call it is a fixed point presentations. When we are adding two B bits, you start adding the bits from right to the left, and you produce the result. Whenever there is a b plus 1 bit occurs at the output, or when there is a carry generated from the MSB bit, we will say that the in uh, in that fixed point addition, the overflow occurs. So there are different ways to deal with that. But here simply I am saying what is fixed point, how to do addition, and what is the problem. The problem is my overflow. Okay, this is what I have concluded with your fixed point. Now coming to your multiplication. That means what I can say in multiplication. When you are adding, when you are adding uh, two numbers, when you are adding two numbers, what we are doing first is we are separating the sign part and the magnitude part. First thing. Now the magnitude of the numbers will get multiplied first, and then the sign of the product is determined. The way you do your multiplication in your ordinary binary arithmetic. You take out the magnitude parts and sign parts, you perform the multiplication of the magnitude number, and then the product will be determined. And the sign will be applied to that result. That means sometimes, in other words, also I can say that when b bit number is multiplied with a b bit number, then the product contains two b bits, right? Two b bits. So again, there is a problem of having, because I am having only 8 and 8, and I may get output of 16 bit, right? Means for 8 bit, 16 bit, this 16 bit I am getting at the output of the multiplication. So definitely again we suffer with the problem in multiplication when we are using a fixed point arithmetic. So to resolve this, one thing is you can do is, let us say you are talking earlier only I said about one number which are integers only integers, not fraction part. Now in case of if you talk about integer fractional part, the number which consists of integer as well as fractional part, in that way, what I will do, I will not multiply this integer fractional into one more integer fraction. What I will do, integer separate, fraction separate, and then we will do the next operation. Now when we are doing so, what we can say, whenever you are, what is the benefit, what is the advantage of having fractional number there, I can say is, when you are multiplying the fractional numbers, always the result will be a fractional number only. That means when you are the important point to note here is, whenever you are multiplying with a fractional number, definitely the result will be a fractional number only, and there will not be any overflow occurs. You multiplied 0.00111 into 0.11011. Definitely the answer will be of a fractional number only. So definitely there is no problem of overflow can occur over here. Okay, so that is about your fixed point in case of addition, in case of multiplication. Now you have to deal with the new topic. And most of the cases, what are in practical applications, in digital applications, we prefer floating point rather than the fixed point because of the problem of addition, of overflow and multiplication of 2b results. And as the binary point is fixed, it is very difficult me to accommodate those number of bits into fit into that register. I have to do a lot of trouble to do that. Now next point is your floating point number. Floating point number. In that floating, what is the syntax? What is the format of your floating point number? Am I audible?
Yes, ma'am.
Yes, ma'am.
Okay.
Yes, ma'am.
Few people are saying my voice is low. Is my voice low?
Ma'am, sometimes it is becoming low and sometimes it is okay, ma'am.
Okay, okay.
Sometimes it is getting disturbance.
What?
It is coming low.
Okay. Now, floating point numbers. We know what is the syntax of your floating point number. Matlab what I meant to say earlier, the binary point was fixed. Now, your binary point will not be fixed. It will be floating according to the uh, desired requirement. Okay. Now, let us see the syntax of this. F equals to 2 power c into m, where m is the mantissa, which is a fractional part, and the fractional part is in such a way that its value always from 0.5 to 1. That's it. I repeat, f equals to 2 power c into m, where m is the mantissa, and that mantissa is a fraction such that its value ranges from 0.5 to 1, and it is always a positive number. And here this c, some people in some books you may find e. Okay, that is a people may call exponent, or people may call it as a characteristics. So that 2c, actually I should write 2 plus or minus c, because this c is maybe either it will be a positive or negative, because you have to deal with the positive number as well as negative numbers, and condition is here it is not a negative number. So definitely we should have this characteristics or exponent as a positive or negative. So f equals to 2 power c into m, where m is the mantissa and c is the exponent or characteristic, which will be either positive or negative. Now let us see how to how to represent my decimal number using floating point number. Okay. Now, for example, I want, let us say f equals to 4 or 4.5. Okay. So let us say I will see only first integer part, then we'll see integer and fractional both. F equals to 4 I want. Okay. F equals to 4. Now this 2 power c, because I don't know the value of c. Here m is what they are saying. It should be, because the range is specified. Either you have to take this 1.2 to 1 only. 1.2 or 1. That means in between values only you have to take. Not less than this, not more than that. So this is fixed somehow. So only this I have to take something. That means let us say your f equals to 4, 2 power c into 0. Let us say, because I have two values, two examples I have taken. One I am saying, let us say your m is 0.5. Let us say m is your 1. If it is 1, it is little bit easy. 0.5 means little bit more calculations you need to do. Okay. Now here 2 power c, because f is known to me. I have taken an example wherein I know f. F is my 4. 4 equals to 2 power c, and here I have assumed the mantissa is a 0.5. Because trial and error only. You have to go on putting the value of your mantissa from 1 by 2 to 1 and obtain your f. Okay. Now here what did I do? 2 power 4 equals to 2 power c into 0.5. Now what should be this 2 power c, so that 2 anyhow it is base. What should be the value of c, so that if I put this, do the square or the triple or whatever the raised to of this 2 and multiply with this, my answer should be 4. So let us say I have taken c equals to your 3. That means 2 power 3 is your 8. 8 into 0.5 is nothing but your 4. Means your LHS becomes RHS now. That means when I put your c equals to 3 and multiply with this 0.5, I will get my answer 4. So this is how I have to write any decimal number using the floating point representation. Suppose let us say I have taken your C equals to 1. Sorry. Yeah. Your mantissa equals to 1 now. Your mantissa equals to 1. Here I took 0.5. Here I have taken 1. Then obviously you will understand that here only multiplied with 1. So what should be the value of this C? Definitely it will be 2 because 2 power 2 is 4. 4 into 1 is 4. So your answer is 4 only. That means here this is how you have to decode, you have to write your number into this floating point number. And moreover here only you won't finish because this f equals to 2 power 3.5. This 3 is a decimal number. You have to represent with a binary number, right? So therefore I can rewrite like f equals to 2. What is 3 binary equivalent? Is 0, 1, 1. Is this the time to get in range? Here, how you are taking the mantissa, right? What is your doubt? How you are taking the mantissa? What they are saying when you are the standard form of that mantissa is value is 0.5 to 1. Now you start with 0.5, go on varying 0.5, 0.2, 0.625, 0.75, 0.85. Any value you are free to take. Only put together your answer should be that. Okay, and always mantissa is a fraction part. That is what you will take
Okay,
your
ma'am.
mantissa. So
Okay, ma'am.
what I was saying is f equals to 2 power 3 into 0.5, right? So this 2 power 3 is what binary representation is 0, 1, 1, and this 0.5. This is also in Desi only. This was in Desi. You have converted. This is your binary. So total answer you want in form of binary. So again, what is your next task is you have to convert this 0.5 into binary, and we know how to convert this 0.5 into binary. If you remember SDLD, what is that you will do? 0.5. You are doing binary representation, right? It is a fractional part. 0.5 into 2, your answer 1.00. Then again multiply with 2, you will get this answer only. So the ultimate way of representing that 4 is this. What is that? I want f equals to 4. How to represent with the help of floating point number is this. That 4 is nothing but 2 power 011 into 0.10. Now let us take one more example. Maybe it will be clear for you. Now, your decimal numbers such as 4.5, 1.5, 6.5, 0.625, and so on. Earlier, I took only fractional part. Now, here I have also integer part. Earlier I took only integer part. Now, here I am having both integer as well as fractional. Now, see here. What I have to represent 4.5. What I have to represent 4.5. Okay, what is the formula? F equals to 2 power c into m. I want 4.5 numbers in this floating point representation. Now, here integer is 4. Means 2 power 2 will be your 4, right? 2 power 2 will be 4. And I have left with 0.5. That means if I take 4 into 0.5 value, definitely my answer will not be 4.5. So what should be the value of this C and M to be taken? I have anyhow my limitation of 0.5, mantissa is 0.5 to 1. So let us, again this is trial and error only I have done. I have taken any value of mantissa, which is 0.5625, 0.5625. You can take any value. You take, like for example, you take only what is your value is 0.5 to 1. It should range. So let us say only you have taken 0.5. Only you have taken 0.5, and take this as C as a 2. 2 power 2 into 4. 4 into 0.5. Your answer is what? I think it is 2, something like that. Then definitely it is not working. So what you do, you just go on increasing the value of either this mantissa or increase the power of this character or exponent, and try to do multiplication and get the desired number. That is what you can do. You have to do little bit trouble over here. What should be the value of your mantissa? Mantissa is from 0.5 to 1. Take any value from that. Take this approximate value of C, like 2 power 2, 2 power 3, to C 2, 3, 4, 5. When you do this, your answer should be that only. If it is coming so, then your answer will be 5. Now here what I have done, I have understood that is 0.5625 into 2 power 3 is my 4.5. But this is what not complete binary representation. So to represent completely as a binary, I am writing this 2, this 3 as a 0, 1, 1, and this 0.5625 again convert into a binary. That means 0.5625 into 2, 1 will take out, again multiplied by 2, 0 will out, again multiplied by 2, 0 will out, out, again multiplied by 2, your 1 will be out. In that way, you get this fractional part as a 0.1001. So this is how you represent your 4.5 numbers with the help of floating point representation. Same way you can do over here also. Here I want only 1.5. So 2 power 1 is 2. Then 2 into fractional part. So definitely if it is more also, if you take this as a more, then what happens? If you take this as a more and quite more and multiply with fractional part, again the result will be less only, right? So you can have an experiment of having the C value more and then multiply with Mantissa, your answer will be compensated. Like here I have taken 2 power 1, nothing but your 2, right? When it is 2 into 0.75, 0.75, because if I am free to take m values from 0.5 to 1. Let us say I took m equals to 1, no? M equals to 1 if I take, then what happens? This is 1, this is 2 power 1. That means total answer will be 2. Total answer will be 2. But my answer is my required is 1.5. So you can take this as a less than 1. This is more and do, or else people can say I will take this 2 power 0 as a 1 and then I'll take some Mantissa value and I'll make my arrangement so that I'll get 1.5. Yes, you can do. You are free to do your own mathematics here. Only thing is you have to maintain the ranges. M is from 0.5 to 1. That's it, the rule over here. Okay, so this is how any decimal number can be represented with a floating point numbers. So how we have done addition and multiplication for fixed point arithmetic. Same way we have to see the multiplication of floating point numbers and addition of the floating point numbers. So when you have the two numbers, let us say f1 and f2, the syntax is 2 power c1 into m1, same. F equals to 2cm, 2cm. Two numbers you are having, f1 and f2, and this is what we can have these two numbers. Now what is my resultant of these two, f1 and f2, is f3 equals to f1 into f2, where when you do this multiplication in floating points, your mantissas will get multiplied and exponents will get added. Okay, when you do the multiplication using floating point, what is the formula for this? Mantissas will get multiplied like ordinary fixed point arithmetic and exponents are get added. And here earlier the mantissas range was how much? 0.5 to 1. But now here, as you are adding m1 and they are multiplying m1 and m2. Now the range is 0.25 to 1. Earlier it was 0.5 to 1, no? Now it is 0.25 to 1. That you have to make a note. So when you are adding the two numbers, it should be the multiplication of the two mantissas and addition of the two exponents, wherein the mantissa range is from 0.25 to 1. Now suppose if it is not satisfying, what not satisfying? Your mantissa is not coming from to 0.25. That means it may be less than 0.25 and it may be more than 1.0, maybe more than 1. So that time, how to solve such a problem is you have to do everything with your exponent part only. You have to go on changing the C1 and C2 in a such a way that your mantissas, your m1 and m2, the product of these two will be range from 0.25 to 1 only. Okay. Now let us take the example over here. We have considered the multiplication of two numbers, 1.5 and 1.25 in decimal number. So what is the resultant of that? Is your 1.875. 1.5 into 1.25 is 1.875. Now I have to multiply using floating point representation. So what I have done, 1.5 to the base 10 I have converted into the floating point representation. Okay, floating point representation. 1.25 also I have considered into a floating point representation, which is something like this, which has come something like this. Okay, you understood how to do this. If not, please practice though it is not so important topic, but they may ask in part A also. So that time it is easy. Only you have to do little bit trouble with your calci to make the arrangement of having the number. That's it. So I assume that we know how to do this. We have done this. We got it. It's 1.5 into floating point representation, 1.25 also in floating point representation. So what that rule says, your mantissa should get multiplied, your mantissa should get multiplied, and your exponent should get added. Okay. So here, what is this? 2 power 001, 2 power 001. That means m1 into m2. 0.1010 into 0.1100, close the bracket, 2 to the power c1 plus c2. Means this is 1, this is 1. 001 plus 001 is 010, right? So 2.010 and multiply these two, you will get this answer. Now you see what is that answer I want. This is to suppose matlab I have to verify, right? Again, how I said my 1.5 to 1.25 is 1.875. I have converted into floating. Then I got my final answer. When I got this final answer, I should be go back to my decimal number, right? So what is this? What is this? 2 power c into m. 2 power c into m. So 2 power c क्या है? This is 2, this is c, this is 2. मतलब 010 is 2. 2 power 2 is 4. This is 4 into this is 0.041. This is in binary form, right? The answer is in binary form. So convert into your desi. What you will do? 2 power minus 1, 2 power minus 2, 2 power minus 3, 2 power minus 4, and 2 power minus 5. When you do so, you will get 15 by 32, nothing but 0.46875. That means this is the value of this. Is 0.46875. Now you can see what you can see 0.46875. Now you see mantissa value is how much now? 0.46875 means it is less than 0.5, right? Then you may say it is wrong. No, it is not wrong, because when you simply represent in the floating point number, you said that your m is from 0.5 to 1. But when you are multiplying the two mantissas, when you are multiplying the two numbers, what you are saying, your range of mantissa is 0.25 to 1. So it is greater than 0.25, right? That means it is not wrong. This mantissa is correct. 0.46875 into 2 power 2, 4. 4 into this 0.46875 will give you 1.875. Okay, that you make note. What is that you are doing in floating point multiplication of two numbers? You are multiplying the mantissas, and your mantissas going to be from 0.25 to 1, and exponents has to get added. And there I said one more thing, that if your mantissa is not in the range, because I said I want mantissa from 0.25 to 1, then so luckily here so I got my 0.46 as a mantissa, so no issues. Suppose if I get mantissa as a 0.1 there, 0.1 there, so that time my mantissa range actually 0.2 to 0.25 to 1, but it is 0.1 only. So what I should do now? I should do little bit trouble to set my exponent. I should take the trouble of uh, changing my exponents. Means I may go for your 2 power. Arey, mute, somebody. Mute yourself. Who's that? Somebody has unmuted themselves and their voice is disturbing me. Why Bhavya Reddy left the meeting in between? Re Bapre. Aishwarya, mute yourself. Aishwarya, mute yourself. So my exponents should get, I should do little bit trouble to this exponent part to get it settled. Okay, so that I can say you in the next example. As you have done your multiplication in floating point, same way I have to see for the addition of this addition using floating point numbers. Okay, so here, the if you because every system will have some advantage and some disadvantage, right? In my fixed point arithmetic, when I was doing addition, it was bit easier to add. Simply go on adding from right to left, and only problem is when the answer, when you are adding two b bits, when your answer get is b plus 1 bits, that time my overflow was occurring. So but there was not much problem more than that, apart from overflow. But in case of this floating point representation, here I had to like take more trouble compared to your fixed point arithmetic in floating point arithmetic for the purpose of addition. So how that we'll see here. Simply when you do this fixed point, hello, why people are unmuting themselves? So when I was doing simply addition or using fixed point, I have taken 3 and that 0.125 number, convert into your binary and simply add it over here. But here, as I said, you have to do little bit more trouble in case of addition for the floating point number. That was a little bit disadvantage kind of thing I can say over here. What was that? You have to first adjust the exponent of smaller number until it matches the exponent of the larger number. Simply I read first, then we'll do one by one. First, adjust the exponent of the smaller number until it matches the exponent of the larger number. The mantis are then added or subtracted. Finally, the resulting representation is rescaled so that mantissa lies in the range of 0.5 to 1. That means the starting whatever mantissa range you had, by default standard one, the same over here, only for multiplication it was 0.25 because two mantises were get multiplied over there. Okay, now here you see what they are saying, adjust the exponent of smaller to larger and something like that. Let us say I am talking about 4 into 10 power minus 2 plus 3 into 10 power minus 3. Now these exponents are not same, and so for addition, what is the rule? These two exponents should be same, it seems. If not, you have to make the smaller number, do the changes in the exponent number in a such a way that it should get same as your largest number. Okay, and then you have to mantissa will get added. Now you see here what I have done. 3.0 and 0.125. 3.0 and 0.125. These are the two numbers you have to get added. So first write it in a binary floating point representation, which is 2 power 2 4 into this, you will get 3. You can verify, cross verify. 0.125 is something like this. Okay, these two numbers, first convert this deci into binary and using a standard floating point format. And then now you see here what you can see, these exponents are not same. This is 2,000, but 2 power 0, this is 2 power 2. They are not same. So we have to do this smaller component, smaller exponent number. We should do something so that we get this equals to this. Means I want to make this 2 power 0 equals to 2 power 2. How to do that? So to do so, what we are doing, you see here. I want 2 power 010 equals to this. Means 2 power 2, nothing but 4. 4, that means this is 2 power 0 into this is giving me 0.125. What my answer should be? It should be always 0.125 only. But I repeat again, what I want is, I have these two numbers to be get added. What I have seen, the exponent of these two numbers are not same. I have to make it same. The smaller should smaller number should be equal to your higher number. Means this 2,000 should get replaced by 2 power 010. means 2 power 2 means 4, right? So that means you want, when you are making this 4, when you are making, let us say simply I wrote 2 power 0 1 0, 2 power 2 4, 4 into this, if I do 4 into this, if I do, sorry, I will not get 0.125, right? Definitely, this answer shouldn't change because this is the actual number which I have to get added. So what I should do so that I will get this 0.125 when I made this 2 power 0 is equals to 2 power 2 now, that I have to see here. So let us say this is my 4 and this is what I don't know. This is what 0.125 I wanted. Okay. Now, what did I do here? Simply your normal mathematics. 4 into something more equals to 0.125, right? Now divide this 0.125 by 4. You will get 0.03125. 0.03125. This is what your Desi representation means. When you multiply this two, your answer will be this, right? So from that, what did I understand? If 4 is nothing but 2 power 2, 2 power 2 nothing but 2 power 010 into what earlier it was the thing 2 power 0 nothing but this into this was my 0.125. Now this is my 4, so this should be what this has changed to 0.03125, which is desi, but I have to convert into binary, right? So convert it into binary by multiplying 2 to take the integer part out. 0.03125 into 2. You do this process, which we'll do in a STLD. Now you got this number 0.0000010. So this is my new number. So 2 power 2 into 0. Blah, 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 whatever I got over here. If I multiply this, my answer is 0.125. So this is how I made my exponents equal. So this kind of only trouble you should do when you have got mantissa not in the range of 0.25 to 1. You have to go on changing your exponent, trial and error, so that you get your mantissa. But fix your mantissa. You got 0.1, no? You want more than 0.2. So let us say you fix for 0.2 only first. Make this as a constant 0.2. Now go on changing this exponent factor, and when you multiply this with that 0.2, your answer should remain same. Like that you have to do. Okay. So what did I do? I got this 0.125. Actual representation is like this. I want to make it like this. I made the same. Now you can see the exponents are same. Now simply add this. Too. So the new sum will be your this. You add this. Anyhow this is the 2 power 010, that is taken common out. Okay. And now this plus this. If you add this fractional part, what you get? 0 0 0 1 1 1 1 1 4 0 0. What was the answer? I got 2 power 010 into 4 into 3. The answer is this, right? I should add. I'm sorry. See here, what I was saying. What did you do? This is 2 power 010. This is also 2 power 010. This anyhow common, same, you have taken out. This is 0.140 and this is 0.0 new one. I was adding this earlier actually. Here, which is not so, because this is the previous one before modification, right? After modification, I got this number, right? So this number, this fractional part, this mantissa part, mantissa parts, you have to get added. What you can see? 0, 1, 1, 0, 0, 1, 0, right? So now when you take this to power 2, 4, 4 into this is binary, converted into Desi, you will get this total answer as your, what is that answer you want? You have added 3 plus 0.125, nothing but 3.125 your answer should be. right? So 4 into this, your answer is 3.125. So you can see here a lot of trouble you have taken to do a simple addition compared to your fixed point arithmetic. That's what I was telling. It is little bit lengthy one compared to your fixed point addition. Okay, but here we can solve the problem of your overflow. That is the main thing. So this is what in a brief about your fixed point arithmetic and a floating point arithmetic. If any question comes from the explain or write the number representations, you can take one example of fixed addition and some mul, and floating point add and mul. Next, or the question may come like compare the fixed point and arithmetic point. Okay, so fixed point arithmetic, floating point arithmetic. It is fast operation, it is slow operation because you have to do lot many things over there, right? Here you have a dynamic range is small, here dynamic range will be more. It is little bit economical, here it is costly, definitely because of more hardware. Overflow occurs in this, overflow doesn't occur in the floating point. And it is used in small computers, it is used in larger or general purpose computers. Okay, so you can anyhow I will share this slide with you, or else you, whenever you are having that any book whatever you are referring, you will find the comparison of your fixed point and arithmetic. Okay, and here main point you see that this round of error occurs in fixed point, round of error occurs in only for addition, whereas round of error occurs in both addition and multiplication. So what is that round of errors and all that we have to see in the next topic. So this is what your fixed point and floating point representation, only number representations.